not only the size of our cosmos, discovering that everything that we thought existed was just a small part of a much grander structure, a planet, a solar system, a galaxy, a universe, and maybe even a hierarchy of parallel universes. But we've also repeatedly underestimated the power of our human minds to understand and even improve our cosmos. Now, to understand what I mean about the first part, underestimating the size of things, we have to remind ourselves of what we humans have managed to figure out so far about our place in space. So let's do that by going for a little ride together here. Let's start in the Himalayas and head up a little bit. When ancient cave dwellers looked up at those sparkly white dots in the sky, they had beautiful myths, of course, for what this was all supposed to be, but I think many of them at the same time felt a little bit melancholy, figuring that they would never be able to know for sure, what the stars really were. But they were wrong. They really underestimated the power of our human minds, because we've subsequently realized that we could figure out the stars, and we didn't even need rocket power, but just mental power, letting our minds fly. With pure mental power, Eratosthenes, over 2,000 years ago, cleverly figured out the size of the Earth to be 40,000 kilometers in diameter. And since then, the same kind of ingenuity has actually given us rocket power. We see here exactly to scale where all the satellites are orbiting our planet right now. The near-Earth comm satellites in green, and then geostationary satellites and others farther out. This is fully to-scale rendering made by the American Museum of Natural History in New York. And as we zoom out farther, and the moon's orbit starts coming into view, where is the moon? You can't even see it, because this is actually exactly to scale. This is not like in one of these kids' books where things are expanded. And this gives us a sense of how vast things are. Our sun, you see here, we all know it takes about 8 minutes for the light to reach us from it, just to get a sense of scale. And as the planets come into view here, we're seeing things which are so big that it takes hours for light to reach us from the outer solar system. Now, I would like you to raise your hands if you know anybody who was born before 1925. So I see a lot of hands. These people that you're now thinking about, they, in a sense, were born in a much smaller universe than us. They didn't know back then that there were other galaxies. What's coming into focus here, the Milky Way, with its hundreds of billions of stars and its majestic spiral structure stretching 100,000 light years from side to side, it only became clear that there are other galaxies in 1925 when Edwin Hubble discovered that. And yet this much grander structure that we're all part of, we now know, of course, is also just one out of billions and billions of other galaxies, which together form even larger structures, groups, clusters, superclusters, and enormous filaments. And we see here the Sloan Great Wall that I and my colleagues discovered in this enormous 3D galaxy map, which is a billion light years from side to side. And that, too, is in turn just part of an even grander structure, what we affectionately call our universe. When astronomers talk about our universe, we don't mean everything that exists, or even all of space. We just mean the spherical part of space from which light has had time to reach us so far during the 13.8 billion years since our Big Bang. Because stuff outside of that, if it exists, if there are more distant galaxies here, no telescope could see them. We would have to wait billions of years more for the light to have time to get here. Now, so far, most of what I said is pretty intuitive. The farther away we look, of course, the more stuff we see. But what on earth is this round ball and with all these funky yellow and green and blue colors? To appreciate and understand that, it's not enough to talk about our place in space. We also have to explore our place in time. Fortunately, that's remarkably easy in astronomy, because looking into the sky is like looking into a time machine. We already talked about how we see the sun, not the way it is now, but the way it was 8 minutes ago. If you see some stars this evening, if the rain clears up, you'll see them maybe hundreds of years ago. So somebody out there looking at us, they wouldn't see us, but they might see the American Revolution or something, or Shakespeare doing his things. And if we look really far out with a good telescope, here we see many galaxies the way they were billions and billions of years into the past. So by simply looking at different distances from Earth, we can actually watch how cosmic history has unfolded. Now, what have we learned from this? Well, we've learned something very, very surprising. And to fully appreciate how surprising these things are, I'd like you for a moment to just imagine that each one of you is a galaxy. And I'm looking at you with my telescope here. What do I see? First, I see something really funny, which is all of you guys here in the front seem like you're about 90 years old. And then I see a bunch of people here, maybe 70, 60, and 50, and I see way up there a row with just teenagers. And then I see a bunch of toddlers. And the second last row is only infants. And the very last row is entirely empty. And as if that weren't surprising enough, the whole back wall of this lecture theater is glowing at me with a strange glow of microwaves. And it's more puzzling still, because for some reason you're all blushing. You guys here just a little bit pink, but those of you in the back look possibly tomato red. This is exactly what we see when we look at these galaxies out there with telescopes. So what on earth does this mean? Well, first of all, why did you seem to order yourself by age as you walked into the lecture theater? Well, we've already talked about how the farther away we look, right, the longer ago we're seeing things happen. So that means that the galaxies that I see near me here are galaxies which are quite old, almost 13, which have been around long enough to mature and grow up and become big and look much like ours. Whereas if I look really far away, I'm looking so far back in the past that galaxies hadn't had time to grow up and mature. We see juvenile and really far away, just these tiny baby galaxies. And if I look really far away, corresponding to the last row of the lecture theater, I see no galaxies at all, because I'm looking at what happened so long ago that galaxies had not yet had time to form. Why were you all blushing? Are you embarrassed to be here tonight with me? Well, we know that if you go down to the highway and you listen to cars, you hear them go, ew, ew. They do not sound, ew, ew. This is because what we know is the Doppler effect, where, as you know, something going away from you has its frequency lowered. Ew. And the exact same thing happens with light. So if a galaxy is flying away, the light frequency will be lower, which means its color will look redder. We call that redshift in astronomy. So the fact that you're all blushing means that all of you guys, for some reason, are flying away from me, which is what we mean when we say that our universe is expanding. I can figure out how long ago you, for example, were right here by just taking your distance and dividing it by your speed. And remarkably, when Edwin Hubble did this for the first time, he found that the answer he got was pretty much the same for every galaxy, because galaxies that were twice as far away were flying away twice as fast. That's why those of you in the back looked more tomato red, and those nearby were just blushing a little bit. So, and when you do the math, you find out that about 13.8 billion years ago, pretty much all the galaxies we see were more or less in the same place. So there was some grand calamity that took place back then. We don't know exactly what caused it, or exactly what happened, but we have a fancy name for it. We call it our Big Bang. We can come back and you can ask me much more about it later if you'd like. But we have a very good idea of what happened during the 13.8 billion years since, because we can see most of this with our telescopes. So what's the last strange thing I mentioned, the fact that the rear wall is glowing? How can we understand that? Well, all this black stuff in space pictures, which I used to think was vacuum when I was a kid, can't be empty space, because the galaxies must have formed from something, right? And we now know that this is mostly hydrogen gas, which gravity later clumped together into galaxies. Now, if everything's expanding, then so is a gas, and you know if you expand a gas, it cools off. That's how your refrigerators and air conditioners work. So as we go farther and farther into the past, this gas must be hotter and hotter and hotter. And if we take an ice cube and we heat it up, it turns into liquid water. If we heat up the water, it turns into, let's have one of the kids answer. What does it turn into here? If I heat up water enough, yeah? Steam, very good. Now, what if I take a gas, like steam, and I heat it up more? What does it turn into? Grown-ups can answer too for this one. Plasma, exactly, which means that the electrons get torn off from the atoms. Now, a plasma is opaque, not transparent like this gas. So it looks to us like beyond all those galaxies and beyond the empty last row where there were no galaxies, we see a plasma screen glowing at us. But it's going to look, of course, exactly the same whatever direction we look, if we look that far into the past. So it actually looks to us like we are surrounded by this plasma screen that we can photograph from inside. And here are some of these remarkable photos of this plasma screen made by the Wilkinson microwave anisotropy probe, a satellite I had a lot of fun working with data from. One of the most successful NASA missions ever. It revolutionized cosmology for a cost of about 25 pence per American. And I just thought I'd mention that, since so many of my American colleagues seem to think that they're spending these enormous sums of money on science when they're actually not. Now, you have to ask yourself, though, when you take pictures of what happened 13.8 billion years ago when our universe was only 400,000 years old, how do we know that they're correct? This is a really hard measurement. Well, you do another satellite, which is even better, and you compare. And the European-led Planck satellite, which just released its data last year, gave us this even sharper image. And it's just astonishing how well it agrees. Look at any one spot here, and it's still there, except now it's not 3 megapixels, but 50 megapixels. Fantastic, fantastic data. So in summary, we humans have kept discovering more and more things about our cosmos and have a pretty good understanding of the last 13.8 billion years. But it's important to not get hubris. We have to be modest also of how much we still do not understand. For example, we've come to realize that we have no clue what 95% of our universe is made out of, and that the part we don't understand is at least 2 separate mysteries, dark matter and dark energy. You can ask me more about that afterwards. We would really like to know, in particular, what the dark energy is, because it's going to determine the ultimate fate of our cosmos, whether it's going to keep expanding forever or come crashing back on itself in a big crunch or something else. We also would like to know more about what really happened early on in this Big Bang, what caused it, etc. There are many things we would like to understand better. So how can we do that? Fortunately, we have only harvested a tiny fraction of all this data yet. It's this data which has transformed the field so much. From when I was a grad student and we argued about whether our universe was 10 billion years old or 20 billion years old, until now when we argue about whether it's 13.7 billion or 13.8 billion. So let me show you how much data we have left to try to collect. If you look inside of this, on the same scale, these beautiful baby pictures of the cosmic micro background, the plasma screen, cover less than 1% of the volume, just a yellow little surface here. And all those galaxies you flew around in earlier are just this dinky little stuff in the middle here. Again, less than 1% of the volume. So most of this is uncharted territory. How can we map that? We can't look here with an ordinary telescope and look at the galaxies because there are no galaxies so far away. They haven't formed yet. Fortunately, there's a very, very cool technique which can do precisely this, which can actually image simply the gas itself and see what it's up to and where there are clumps of it, etc. Because hydrogen gas turns out to give off radio waves. They're 21 centimeters long when they're emitted, and by the time they get here, the expansion of the universe has stretched them to longer wavelengths. So by looking at how long they are when they get here, we can figure out where they came from and make amazing 3D maps here in principle. It's very hard. No one has succeeded yet. A bunch of teams across the planet are competing to try to do this. We are part of this competition at MIT, and I want to show you in just 2 minutes how to build your own radio telescope. That was easy, huh? Thank you. It's one of the most fun things with being a scientist is to get to work with so many awesome students and other researchers who are just so inspiring. And another thing you notice about this is there were no moving parts at all in this telescope. It doesn't look at all, in fact, like one of those big radio dishes that you saw. Have you seen, raise your hand if you saw GoldenEye, the Bond movie, for example, where the Arecibo telescope was in. It's because we've discovered that using a technique that George Ryle here in Britain invented, you can, instead of building expensive dishes, just buy a lot of mass-producible small antennas and cover a large field with them, and just measure the volts in all of them, and then feed all those volts after careful amplification into some really massive computing equipment and have the computers just figure out what the sky looks like. And since computers are so much cheaper now, that turns out to totally be the way to go for building really large radio telescopes like this. We can image not just a small part of the sky at a time, like traditional astronomy, by pointing your telescope, but we can figure out what the whole sky looks like, boom, all at once. And here is a bunch of the friendly students who I worked with to build this, and we're now joining forces with some more colleagues to build one of these, hopefully that covers about 1/10 of a square kilometer, which should help tackle further many of these open mysteries that I mentioned earlier about dark matter, dark energy, our origins, and our ultimate fate. Now, I told you in the beginning that I feel we humans have been the masters of underestimation, and how we've again and again realized that everything we thought existed was part of something bigger, but how at the same time we had underestimated ourselves and our ability to understand things. And it really is quite remarkable to think that those same cave people, maybe who didn't think they could ever really know what the stars were, we're no smarter than they are, but we've now managed to figure out in quite some detail what happened during the last 13.8 billion years. So why is that? How have we humans been able to figure out so much? Partly, of course, it's because the human mind turned out to be even more amazing and versatile than they thought. After all, they hadn't even imagined that you could do such a thing as writing and so on, let alone invent telescopes or program computers. But I think there's more to it as well. We've discovered two extremely powerful ideas in science, and both of them were, in a sense, first really established firmly here in London, and partly here in this building. The first one was, do experiments. And the second was, once you've done experiments, use mathematical modeling to try to describe the data that you see. And we've almost gotten so used to this in science that we forget to ask why this works. But I want to ask why this works. I explore this a lot in the book. And I think the reason it works is because nature turns out to encode all these hidden mathematical patterns and shapes and regularities. So this approach of experiments and mathematical modeling helps our minds find these clues, these mathematical clues, which we can then use to predict the future better, to develop new technologies, and so on. And this is a very old idea, of course. Pythagoras, over 2,000 years ago, said that numbers seem to rule the universe in some sense. And about 400 years ago, Galileo said that our universe is a book written in the language of mathematics. But where is all this math that these guys are talking about? I mean, I look around in the room, I can't even see any numbers anywhere. And when we look at Galileo's quote here, though, we see that although many people think of math mostly as a bag of tricks for manipulating numbers, or maybe, like my mom, think that it's a sadistic form of torture invented by school teachers to make us feel bad about ourselves. Galileo thinks of math in a broader sense. He talks here about shapes and patterns, and of course, geometry is a key part of mathematics, and modern math books often don't even have any numbers in them at all now. It's much more abstract than that. And shapes and patterns is certainly something we have a lot of in nature. Right? If we throw an object and it moves under Earth's gravity, it always moves in the same shape. What do we call this shape? A parabola, exactly. And it's described by a very simple equation, like y equals x squared. whenever we look in the sky at things moving under gravity, again, they all move in a simple shape, regardless of whether they're orbiting a star or a black hole or something else. So what do we call this shape? An ellipse, exactly. It obeys, again, a very simple equation. And moreover, these two shapes are related because if you look at a very tiny part of an ellipse, it's very well approximated by a parabola. And if you do this traditional school math problem of figuring out how an object moves here, more carefully, you see it's actually not the parabola. It's actually exactly a piece of an ellipse, which Isaac Newton first showed. And I have a very bad habit, because I'm a physics professor, which is I love giving unannounced pop quizzes. So you're going to get one too now. But don't worry, it won't contribute to your final grade. It's just diagnostic. So here are three discoveries. The discovery of Neptune, discovery of the radio wave, discovery of the Higgs boson. What tool was it that triggered the discovery of these three things? Any takers? This is a group quiz. Yes, I'll just shout out. Maths. Exactly, it was maths. Or if you want to be really finicky, you could argue that it was technically the pencil, because they were all predicted from mathematical calculations. Adams here in Britain and Urbain Le Verrier in France realized that the planet Uranus was just not moving according to Newton's equations quite exactly as it was supposed to. So they calculated and calculated and calculated, and one of them wrote a letter to this astronomer Gall in Berlin and said, hey, point your telescope at such and such a direction in the sky at such and such a time and you'll find a new planet. I don't know what Gall thought when he got this letter. Maybe he thought that this letter writer must be cuckoo for Cocoa Puffs. But he was certainly curious enough to try, and boom, there was Neptune, predicted through mathematics. And just a few decades later, here in Britain, James Clerk Maxwell was studying realized that he could unify all of electricity and magnetism in the Maxwell equations, and he did more calculations and predicted that if you built a certain kind of device, then you could use it to send information at the speed of light through empty space.